had a good break. It looks like summer is finally over. So it has started getting a little cold. So we had been looking at fault modeling. And the reason behind it is that we want to convert the problem into something that can be managed, as opposed to a problem that is too big to be that we cannot handle. And basically, I was mentioning that fault models are based on what we believe are the most common failure mechanisms. And our hope is that a fault model will represent most of the faults, if not most of the actual defect types, if not all of them. And I was mentioning about the single fault stuck at 0-1 model. Now this is the classical fault model, and I was mentioning about the single fault assumption. I guess we can call that part of fault modeling, because a fault model is an assumption. And other gate level fault models, so these are gate level, so this is gate level. Another gate level fault model is the delay fault model. And we had looked at it last time. And basically, if you have excessive delay, then it will cause the response to arrive too late at some destination storage elements and may not be latched correctly. And we have seen that to test for a delay fault, you need to have pairs of vectors to make sure that you can propagate a transition. Remember, in order to have a transition, you need to have at least two pairs of vectors. So make the transition pass through the circuit and catch the transition at the end, and that would be a test for a delay fault. And then we were looking at transistor level faults. And so we were looking at stuck on and stuck open faults. And last time we were looking at an example where so we saw an example of, this is the circuit we were looking at. So this is a 2-input NOR gate. And this is ground, so let's call this low, and this is high. So this is your VDD, as electrical engineers call it, and this is ground. And here is input A, and here is input B, and let's call this one, this is PA and PB, let's call this NA and NB. And here's the output. And now last time we had seen one case when PA is stuck open. When this is stuck open, then output is basically, it will never go to 1, so output is effectively stuck at 0. And then we had looked at the case when NA is stuck open, and in that case we had seen that in order to test that you are going to need a pair of vectors. And we are right now looking at the case where PA is stuck on. And this is the case we were talking about. Now what will happen when PA is stuck on, and let us say that we want to test it. So in order to test it, we would apply A and B equal to 1 and 0. And in that case, normal output would be 0, but what about the faulty output? So this is stuck on, and PB is closed. So you have a direct path between here and here. And here, these are N-type, so you have a direct path. Oops, sorry. N-type, so if it is 1, that is closed. You have a direct path here. So notice that in this case, you have a direct path between here and here, and between here and here. So you cannot say what the output would be. So basically, you have a voltage divider arrangement, and there are two low resistance paths between high and low, VDD and ground, and would depend on what is the relative resistivity, which, as I was mentioning last time, would depend on dimensions. Now, when they build these things, they use some approaches for optimizing a few things that require them to specify the dimensions. But in general, unless you are the designer, you would not know the dimensions. So you would not know the right answer. However, notice that you have a low resistance. Between high and low. Now these are your two supply terminals. High is VDD and low is ground. So you have a very high supply current. And it is called IDD. IDD is the supply current, Q is the quiescent. So even when the circuit is not switching, Q is for quiescent, that means when it is not switching. So normally this is very close to 0. But in this case, this goes up by an order of magnitude higher. So if you are monitoring the supply current, then this type of fault is easy to detect. Provided the normal supply current in the circuit is not too high. Now this could be a difficulty in very large circuits where ordinarily the supply current is very high. So the chips today, the processor chips today draw a large amount of current. So it may be hard to see elevated current, but even now, because this would be an order of magnitude higher, that makes this very visible. And all chips today they are tested for high supply current, and there are a couple of reasons for that. One thing is that if you have high supply current, then that would mean that either you have some stuff on, or you have possibly a short. Let's look at a situation of a short. Any questions on this? Okay, let us assume that we have let's use the simplest gates that we can. What is the simplest type of digital gate you can think of? Inverter, right? Okay, so let's take two inverters. It will be easy for us to draw the diagram. So here is an inverter. And let us say the input is low, so the output is basically, because this is low, so here this would be high normally. And let's assume here we have another inverter. Where you apply input 1. So normally the output would be a 0, in other words a low. Now what would happen if there's a short between these two nodes? So now those of you who are electrical engineers, they will know that whenever you have two logical connections like this, some signal coming from here, some signal coming from here, and you're connecting together, it is generally an invalid connection, except in some special situations, because you have to know which is going to win, high or low. And again, it would depend on the transistor dimensions. So we don't know what the voltage would be. So we don't know what is going to happen to these two nodes. However, notice that you are going to have this is 1, so this would have been low. Notice that you have here a path which is low resistance between that high and this low. So since, notice that this was supposed to be high, that means it is connected here. This is supposed to be low, that means it is connected here. And since they are connected, this means this is connected here. So again, in this case, you have very high supply current. So if you are monitoring the supply current, that is a very good test for shorts. Now remember, notice that this type of short, it would be very easy to detect. All you need to do is to apply two different values here. So as long as the two values shorted are of opposite value, this would be detected, provided you are monitoring the supply current. Now there's as I was mentioning, people now regularly test the chips for very high supply current. And it is highly effective for faults of this type. We have done over many years, we have done a lot of work on transistor level modeling, including we were the first researchers to suggest that monitoring supply current can be an effective way of testing. At that time, people thought that, now we are academics, of course, so people thought that it's just an academic idea and would have no practical value. But within a few years, people agreed that for some of these faults, there is no definite way of testing if you monitor only the voltages. And so now supply current testing is always done.